Alright, I've been trying to work this video. It's been too long over the summer. Anyway, this is your summer review of what we did this summer. Some of you did it with me in June. We're doing this in class. This is for you if you need to go over a question again. If you need support, this is what it's there for. Alright, so let's go through the questions and I'll do my best to explain it. Describe the end behavior of each graph in limit notation. So the end behavior is what the left and right end are doing. So you can see that the end behavior here is going to a number. So the y value that it's going to, there's a horizontal asymptote here, is -1. So to write this in limit notation, the right end behavior, you would write down as x approaches infinity. So this is a limit notation as x approaches infinity. You can't equal infinity. That's the power of a limit. It's approaching infinity of what? Of this function. And then what's the answer? So the right end behavior is -1. We also want to write down the left end behavior. That's as x approaches negative infinity, again, of this function. And the left end, again, is the same number, the y value -1. Look at number 2. Understand what you're looking at when you're looking at the graph, and what's the right end and the left end. So the right end, again, is going to a y value. That's 1, 2, 3, 4, 5. That's 5. So the right end behavior is written as the limit as x approaches infinity of that function is equal to 5. On the other side, this end behavior, the left end, we write as x approaches negative infinity of the function, and the left end infinity is going down forever, so that is negative infinity. So that's writing end behavior as a limit. If I look at questions number 3 and on, I'm asked to evaluate a limit. Now, sometimes when you evaluate a limit, it's as simple as understanding how to substitute in, while other times you have to do a little bit more work to understand really what's happening here. So if I substitute 3 into here, I'm really interested in the denominator to have an understanding of what's happening, and possibly the numerator to know what's happening. So if I can, I will factor it, because often just factoring gives me a better view of what's happening. In the denominator, 2 numbers that multiply to 3 and the same 2 numbers add to -4. That's -1 and -3. If I look at the numerator, I know I can factor out a -2. That gives me x squared plus x minus 2. Again, I can actually factor this out. It just gives me more information when you factor it, and it's good practice too. And then we'll say what that little negative means on the 3 in a minute. So if I look at here in the numerator, 2 numbers that multiply to -2 and add to 1. So that's going to be +2 and -1. They multiply to -2, but they add up to +1. And we still have a -2 in front. And then the denominator. All right, what's going to happen if I just plug 3 in? I want you to notice that 3 is a discontinuity. If I plug 3 in for x, 3 take away 3 is 0, and 0 times any number is 0. We have a 0 in the denominator, which makes a discontinuity. So I can't just substitute in and get an answer to evaluate this limit. Now, from the left means this, that when I think of the graph at 3, 1, 2, 3, there's an asymptote at 3. It's non-removable, so there's an asymptote there. And the question is, to the right and to the left, what's happening? So at a vertical asymptote, it's either going to go to infinity or negative infinity. So if I plug in a number that's larger than 3, like 4, and I do the work, I want you to notice this -2 will make the answer negative. So this graph on this direction is going to negative infinity on the right. It's an odd asymptote because the exponent is odd. So on the other side, it's going in the opposite direction. So 3 from the left, what direction is it going? So we can say the answer is infinity, or we could say because you can never approach infinity as such, that this limit does not exist. Both are correct answers. When I look at number 4, I want to know what the limit is as x approaches 5 from the right. Now, if I can factor this, the numerator, I might have more information that might be helpful. So if I look at the numerator, I'm going to factor out a 2, and then recognize I'm left with negative x plus 5. Now, you might recognize this negative x plus 5 does simplify with the denominator, but we do have these absolute value bars. Now, what this is going to be is that what's the answer when I plug in different numbers? Like, let's say I plug in 0, you would get 10 divided by 5. That's 2. Let's say that you plugged in 3. If I plug in 3, negative 3 plus 5, and negative 3 plus 5, you're going to get the answer positive 2. Now, is there any chance you will not get the answer positive 2? And if you plug in a number bigger than 5, so if you plug in positive 6, you're going to actually end up with a negative answer. So even though they cross out, you'll get a negative 2 with that. So if I graph this for you, all numbers up to 6. So 1, 2, 3, 4, 5, there's 6. All numbers up to 6 is going to give you the answer positive 2. Exactly there. And then at 5, actually, so negative 5 plus 5, it's indeterminate to actually be a whole at 5. So let's do that accurately. So there's a hole there. Now, if I plug in a number bigger than 5, you actually get the answer negative 2 every time. So if you plug in any number bigger than 5, you're going to get the answer negative 2 instead of positive 2. So the limit as x approaches 5, there's a jump here. But on the right, this is here, what's the y value on the right? And the answer is negative 2. On the left, the answer would have been positive 2. All right, these are going to get easier. The limit as x approaches negative 1 of this. Now, when I plug in negative 1 plus 1, you can see that it's 0, but it's not indeterminate, meaning it's not 0 divided by 0. So negative 4 divided by 0 is undefined. That means this limit does not exist. If I do the same thing here, I get negative 1. So in other words, I'm substituting 0 in and evaluating. I get negative 1 over 0. Again, that's undefined. So that means it does not exist. This is called a piecewise. So when I'm looking at 2 from the right, I'm only looking at it when it's greater than 2 here. So I'm going to plug 2 into the bottom piece. 2 take away 9 is negative 7. And that's it. If I look at number 8, as x approaches negative 2, again, it's going to be helpful if I can factor this to get more information. So I'm going to help that out. So I'm going to factor out a negative 4. I got x squared minus 4. That can be factored further. Factor out an x. And I have x squared subtract x subtract 6. Again, the limit as x approaches negative 2. I'm going to keep factoring here. So the top, x squared take away 4 is a difference of squares. Square root each one, and you have x plus 2 and x subtract 2. The denominator, 2 numbers that multiply to negative 6, and the same 2 numbers add to negative 1. That'd be negative 3 and positive 2. Now, I want you to notice here, sure I factored everything correctly, that x plus 2 is removable. Now, when I plug negative 2 into here, I can actually now evaluate the limit. So when I evaluate this limit, negative 2 take away 2, that's negative 4 times negative 4, that's 16. If I substitute negative 2 here, negative 2 take away 3 is negative 5. So negative 2 and negative 5, they multiply to positive 10. That's a great answer. You could reduce it down. That's a great answer. And there you go. For number 9 and number 10, I'm going to give you a break. So with trigonometry right now, I could have you use a calculator. But right now, we're not focused on trigonometry and calculus, so I'm going to let that pass right now. Number 11. In number 11, we're evaluating each limit again. Ultimately, we want to evaluate a limit with the number given. So as x approaches negative 2, so if there are no discontinuities, then it's just a matter of substituting in and evaluating. This is a calculus definition of continuity. If the function value and the limit value are the same number, it's continuous. So first, negative 2, there are no discontinuities here. So you can just plug negative 2 in for x and evaluate. What is that? That's 8 minus 16 minus 14. So negative 8. Just work this until you have an answer. And this is 8 take away 30, right? That's negative 22. Here, again, what I'm looking for, does 5, is that a discontinuity? So if I plug 5 in the denominator, will that make the denominator 0, a discontinuity? And it doesn't. So you can just evaluate at that number. Make sure you do it as accurately as possible. So first you square and then the negative. So this is negative 25, take away 2. And then 30. You could divide by 3 and get negative 9 over 10. Number 13. I want to evaluate this limit. So at negative 1, it's not a discontinuity. So you can just evaluate it. This is a negative times a negative. So it's 7 plus 2. That's the square root of 9. So that's 3 plus 1. And there's where 4 comes from. Number 14. Again, this is a continuous function. So just plug 2 in and get your answer. So 2 take away 4 is negative 2. Just as a reminder, a negative exponent does not give you a negative answer. So it means reciprocal. So 4 squared is 16, and it's the reciprocal. And that's fine with me if you just put them beside each other. Number 15 and number 16 are trigonometry questions with calculus. I'm going to let that pass right now. I know you're thankful for that. Number 17, again, it's helpful to factor first to be able to see it better. So if I ask you to factor the numerator, could you do it? 2 numbers that multiply to 8 and the same 2 numbers add to 6. Now the denominator, the first thing I notice is there's a common factor. 2 goes into each term. So divide out a 2. And then you can factor further after that. So 2 numbers that multiply to negative 12 and add to 1 would be positive 4 and negative 3. I want you to notice that positive 4, it is removable. So that means there's a hole there, so the limit exists. And now we evaluate at negative 4. So negative 4 plus 2 is negative 2. Negative 4 take away 3 is negative 7 times 2. And then we could reduce that down and get the answer positive 1/7. Number 18. Again, my first step here is to factor. I do notice if I plug in positive 1, I do get the answer 0 in the denominator. So it is a discontinuity. at 1, but we're going to factor see if you can remove the discontinuity. So when I look at this is called a cubic. It has 4 terms. I want to see if I can factor this by grouping. So I'm going to look at the first 2 and factor out an x squared. I'm going to look at the next 2 and factor out a -1. When I look at the denominator, there's a common factor of 6x. Now I'm going to continue to factor. So x subtract 3, and what's left over is x squared subtract 1. The denominator is already fully factored. One more step in the numerator. X squared subtract 1 is a difference of squares. So the square root of x squared and the square root of 1. So we have x subtract 3, x plus 1, x take away 1. Now what I want you to notice is x subtract 1 is now removable. So I can now plug in positive 1 and get an answer. So positive 1, take away 3 is -2. 1 plus 1 is 2. And then 6 times 1 is 6. So this is -4 over 6, or -2/3. All right, number 19. If I evaluate this and plug 4 in for x, the square root of 4 is 2, and 3 times 2 is 6, and 6 take away 6 would make it 0. It is not continuous. There's a discontinuity at positive 4. So one way to remove a discontinuity is to use what's called the conjugate. So 3 root x plus 6, top and bottom. So I'm going to multiply by the conjugate. The numerator, I'm just going to write them beside each other. The denominator, I'm going to go, this is now what's called a difference of squares again. All you have to do is multiply the first term times the first term. So 3 times 3, that's 9, and root x times root x is x. And then -6 times 6 is -36. The denominator now factors. So if I look at the denominator, 9 goes into both evenly. So factor out a 9. And then by factoring that out, we can now remove the discontinuity. So x subtract 4 is now removable. I can now evaluate at 4. So the square root of 4, that's 3 times 2. So it's 6 plus 6. That's 12 over 9. Or another way to write that is 4/3. Number 20. Step number 1, evaluate at -1. So -1 plus 5. So the square root of 4 is 2, and 2 take away 2. That's 0. -1 plus 1 is 0. This is indeterminate. 0 over 0. All right. We are going to use what's called the conjugate here to remove the discontinuity if we can. So we're going to go root x plus 5 plus 2. That's called the conjugate. Top and bottom. Now, when I write this limit again, the numerator I'm going to multiply out. So root x plus 5, root x plus 5, the square roots remove, and that's what you're left with. -2 times 2, that's -4. And then the denominator, I'm just going to put them beside each other. Now, 5 take away 4 is 1. This is x plus 1. These remove. And that when everything's removed, the number that's left over in the numerator is 1. And then I'm going to plug -1 in and now evaluate. So we have 1 on top. This is -1 plus 5. Plus 2. So -1 plus 5 is 4. So the square root of 4, that's 2 plus 2. So you get 1/4. Number 21. These questions have to do with end behavior. So the limit as x approaches -infinity, this is saying, hey, where's the left end going? This is a polynomial. To know end behavior, the power term, the term with the biggest exponent, is what I look for. And what I'm looking at is the power term is positive and it has an even exponent. That means both ends go up. Positive with an even exponent. So the left end and the right end are both going to infinity, and you have your answer. For number 22, what's the right end behavior here? This is a rational function. So first of all, this is telling me right end. For a rational function, again, it's power term over power term. I want you to notice the power term in the denominator is more powerful than the power term in the numerator. When the bottom is more powerful, both ends are going to 0. It's another way of calling a horizontal asymptote. So again, what did I look for? The denominator is more powerful than the numerator. So therefore, when the denominator is more powerful, the end behavior is 0. For number 23, again, I'm looking for the right end behavior. For this one, I have two power terms. The top is more powerful, so I have to simplify it down. So it's power term over power term. Then, when I simplify this down, I get negative 1/3 x. So x makes x squared just an x. You could also write it like this. And what I want you to recognize is this power term that it reduces down to is just a line with a negative slope. So negative 1/3 x is a line with a negative slope. So the right end is right here. So because it has a negative slope, the right end is going to negative infinity. Number 24. The limit as x approaches negative infinity. So negative infinity would be the left end. Power term over power term. Oops, and the negative matters. So when I look at the power terms, it's 8x over negative 10x. This reduces down to negative 4 over 5. And that's the end behavior in both directions. So when they're equally powerful, whatever it reduces down to is the end behavior, and that's your answer. Number 25. We're almost there. 2 pages. Okay. We did not talk about sequences, so that's super easy, right? So we're not going to do 25 and 26. Number 27. Given this function, find the slope of the tangent line to the function at that point, and then write the equation of the function in slope-intercept form. Now, we're not told to find the derivative in a certain way, so I'm definitely going to use shortcuts. So I'm going to do the power rule here. So to find the slope of the tangent line, it's the derivative of this. And so that's the symbol for derivative. The power rule is you take the exponent times what's in front. So 2 times negative 2, and then subtract 1 to the exponent. The derivative of negative 16x is just negative 16. And the derivative of negative 29 is 0, so it doesn't need to be there. Next, we take the x value, which is negative 2, and we plug it into the derivative. So that's negative times a negative. That's 8. Take away 16, that's negative 8. What we just found was the slope of the tangent lines. We're going to write that down right there. Next, I want to find the equation. And I won't even worry about slope-intercept form. Just the equation of the line. So I need to know the x value. I need to know the y value. Now this comes from the question, the x and the y. We just found the slope to be negative 8. And now I want to write the equation that goes with those numbers. So the equational line would be y equals, you start with the slope, and then it's x plus 2, subtract 5, and it's done. All right, 28. Given that function, find the derivative of the function using a limit. All right. So I need to know the limit definition of a function. So how do I use the limit definition? Let me remind you that the limit definition of the derivative is slope as you take 2 points and it becomes 1 point. Okay, so this is the formula that we're going to follow. So there's the limit definition of a derivative. So there, I want to know the derivative. That's what we're going to follow. So the limit as h approaches 0. We're first going to substitute x plus h in for x. So it'd be x plus h squared, and then minus 7, and then again x plus h. And then we're going to subtract. We're going to use parentheses, and then I'm just going to put the function inside the parentheses. That's x squared subtract 7x. And then the denominator is just h. And we're going to use algebra to remove the discontinuity and then find the derivative. All right, so in the numerator, we're going to expand it. X plus h squared. That's x plus h times x plus h. If you expand it, this is what it's going to look like. And then I have negative 7x. I have negative 7h. And then I have negative x squared plus 7x. That was the hardest part. Now we get to cross things out. So x squared and negative x squared, negative 7x plus 7x, they all cross out. What's left, I'm going to factor out an h. They have a common factor. And what I'm left with is 2x plus h minus 7. Now the discontinuity can be removed, and now you plug in 0 for h, and you're left with 2x minus 7. And then evaluate the derivative at 3. So if I want to evaluate the derivative at 3, plug 3 in for x and evaluate it. So that's 6, take away 7. So here, what's the derivative? 2x subtract 7. And then if you evaluate the derivative at 3, the answer is negative 1. All right, last page. We're going to use only derivative rules here. So these are the power rules we're using. So the power rule here to find the derivative, you take the exponent times what's in front. So that's 28, and then subtract 1 to the exponent. Multiply, that's negative 16, and subtract 1 to the exponent. Negative 11x, that leaves you with negative 11, and then the derivative of 5 is 0. For number 30, we're going to rewrite this. So the fourth root of x is this. When you multiply it together, you add the exponents. So the exponent you don't see is 1. When I add them, you're actually going to get 5 over 4 when you add them with common denominators. Now, I'm going to multiply the exponent times the number in front. How do I do that? So 12 times 5 over 4. So 4 goes into 12 3 times. And 3 times 5 is 15. And then subtract 1 to the exponent. Well, the shortcut to do that is 5 take away 4. That's positive 1, and use the same denominator. And there's the derivative. Here, we're going to write this exponentially. Square root means the denominator is 2, and then the power of 3 goes in the numerator. And now again, we're going to use shortcuts. We're going to take the power times in front. So 4 times 3 over 2. 2 goes into 4 twice. And then 2 times 3 is 6. And then subtract 1 from the exponent. So again, the shortcut for that, 3 take away 2 is positive 1 with that common denominator. Number 32, we're going to reduce this down first. So I'm going to separate this. We have 15x to the 6th, 3x to the 4th, and then we have minus 3x over 3x to the 4th. So I'm going to reduce this down first by separating them into two fractions. So 15 divided by 3, that's 5. And then subtract the exponents, that's 2. 3 divided by 3 is 1. And then 1 take away 4 is negative 3. So it's really x to the negative 3. We don't want to write it as a fraction. If we can avoid it, we'd rather write it with the negative exponent and then follow the rules. So 2 times 5, let's write down derivative. 2 times 5 is 10. Subtract 1 to the exponent. A negative times a negative is positive 3. If you subtract 1 to the exponent, it's negative 4. In this example, we're going to multiply it out first and then take the derivative. So we're going to FOIL. First times first. So that's 8. And then add the exponents. We're going to go first times the middle. That's negative 2x to the 4th. First times the last. That's 12x cubed. Now we're going to do the same thing with the second term. So negative 3 times 4 is negative 12x to the 3rd. Make sure I'm doing positive 12x, negative 12x. Yep, they're going to cross out. Negative times a negative is positive 3x squared. And a negative times a positive is negative 18x. Now we're going to combine like terms. We have 8x to the 5th, negative 2x to the 4th. These cross out. We have 3x squared minus 18x. Now we can take the derivative. So the derivative would be 5 times 8, and then subtract 1 to the exponent. 4 times negative 2, subtract 1 to the exponent. 2 times 3, subtract 1 to the exponent, and negative 18x is just negative 18. Number 34, I'm going to factor this. I'm not sure. This is what I'm going to end up doing. You know what I'm going to do? So this one requires a rule called the quotient rule that I haven't taught you. It's another shortcut that you're going to be learned soon. And so I'm not going to go through a painful process of how to take the derivative when we have a rule to use when we're dividing. And I just haven't taught you the shortcut yet. So we're going to not do that, but that's a lesson coming up. All right, from 35 on, we're going to use our calculator. So press pause if you like and find your calculator. And then we're going to do that. So it says the average population in thousands from 1970 to 1990 can be represented with this function where t is the number of years since 1970. So what is the average change in population? That's the word average rate is finding the slope between 2 points. That's 1980 and 1990. So I'm going to find the slope between that. Now, 1980 is 10 years after, and 1990 is, oops, I'm going to do that first. Let's do this right. So 1990 is 20 years after 1970. 1980 is 10 years after that. And then in the denominator, so this is basically y2 minus y1, and x2 subtract x1. And now I'm going to use my calculator to do the work. Now, I'm going to teach you again something to make it a little bit easier to work with. I want you to turn on your calculator, and we're going to define this function first. So we're going to pretend like we're going to graph it. I'm going to actually erase this. Press tab, and then we're going to put this in. So again, on the home screen, see this button that looks like a shaky calculator? Press it. And if you have something there that you want to erase, press menu, press actions, and then delete it all. Press number 4, and it all gets deleted. And then press tab, and then you can type it in. So we're going to type it in with X, not T. So 0.03x cubed. Move the cursor over. Subtract 1.5x squared plus 20t. So you can see it. It's going to be x plus 80. And then once you have it typed in, press enter. And now it's defined. That's what I really wanted to do. And then I'm going to press that shaky calculator button again. And now we're going to evaluate it. So I want you to go control and then divide. That's a fraction. And then I want you to type it in. Now in the calculator it's defined as F1. So I'm going to go F1 20, subtract F1 10. And then in the denominator is 20 take away 10. And I want you to notice the answer is minus 4. Now, the answer is in thousands. So because it's in thousands, right, minus 4 means minus 4,000. So the answer is B, minus 4,000. It says, what is the instantaneous rate of change in 1973? Well, for 1973, that's 3 years after. An instantaneous rate of change means the derivative. So what I want to know is the derivative at 3. How do I do that with my calculator? So it's already been defined. So how do I find derivative? I want you to press menu. Make sure it's focused in here. I want you to press menu, and then calculus, and then derivative at a point. So number 2. X is our variable. Our value, like what number do you want to evaluate at, is 3. And then I just type in F1 at X. That's what I'm taking the derivative of. Press Control and then enter. And you get the answer 11.81. Now it's in thousands. So 11.81. I actually have to move the cursor 3 to the right, so the answer is A, 11,810 people per year. All right, 2 more left. We have a new equation we're going to use, so we're going to put that in our calculator. Oh, the numbers are small enough we don't have to. But what is the average velocity of the ball between 0 and 2 seconds? So here's an equation that describes a ball being thrown up. H is height, and T is time. And to find velocity, or average velocity, that's the change in height over the change in time. So let's make sure we know what that means. So the velocity is the change in height over the change in time. When it's between 2 points, we are finding the slope. So that's like h at 2 minus h at 0 over 2 take away 0. So average velocity is like finding slope using slope formula. y2 minus y1, x2 minus x1. Now I'm going to substitute in. If you substitute in 2 for t, you get 148. If I plug in 0, that's really easy. I get 92. And obviously 2 take away 0 is 2. Put this together, and the answer is 28, and it's feet per second. So the average velocity is 28 feet per second. For question number 38, what is the instantaneous velocity of the ball at 4 seconds? For this one, we're going to take the derivative. So I want to take the derivative here. So the derivative of 92 is 0. The derivative of 60t is 60. And then 2 times negative 16 is negative 32t. So take the derivative and then plug in 4 and find the derivative at 4 seconds. So 32 times 4, that's 128. 60, take away that, you end up with the answer negative 68. So the ball is falling, so that's why it's negative. It gives you direction. and that's feet per second. So at 4 seconds, this is the rate, negative 68 feet per second. Done. All right, that's it. You did your review for the summer. We're ready to go forward. Keep asking questions to me. I'm super proud of you for doing your work. Mr. G Math, over now.